Hello, my name is Klaus Scheffler and I would like to report on our recent paper higher resolution mapping of neuronal activity with balanced SSFP at 9.4 Tesla. And I did this work together with bSSFP, who is the last author on this paper. So the basic idea is from this paper here that we published about 15 years ago. On the left top you can see the balanced SSFP or TrueFISP signal profile. And what we did 15 years ago, we did imaging at the stop band, which is very sensitive to small frequency changes that are induced by oxy or deoxyhemoglobin, and therefore depends on the functional activity. So the frequency change is about 5 Hz at 1.5 Tesla, and we were able to detect some signal changes of 8 to 10% in this experiment. So this principle was then repeated by several other researchers, again in the stop band using smaller flip angles and therefore also with some increased signal intensity. But this is a very sensitive method as we work in the stop band, which is a very narrow frequency range. Then in 2005, Bowen actually in an ISMRM abstract presented for the first time TrueFISP or balanced SSFP functional imaging in the passband. So we are in a much broader frequency regime, and therefore the functional response is much more stable than in a stop band. And again, this principle was repeated by several other groups showing robust activation of a balanced SSFP fMRI signal even at fields of 3 Tesla and 7 Tesla. So as you know, balanced SSFP is very sensitive to frequency offsets. You can have these bending artifacts, and therefore it was not very obvious to go to 9.4 Tesla because at this field it's even more sensitive. But still, this is an example. We were quite successful to generate these activation maps in the visual cortex. So we presented a checkerboard and very simple paradigm. And this is a relatively small region that we cover here, about I think 16 slices. And in this region we were able to have bending free images using the conventional shim up to second order. So if you confine your region of interest to small volumes, it is no problem with a repetition time of 3 or 4 milliseconds to get bending free images, at least in this region. Also we went to higher resolution, 0.8 millimeter isotropic, resulting in a little bit longer repetition time of 4 or 5 milliseconds, and even then it's possible to have no bending artifacts. So a very interesting question is of course how does this compare to gradient echo EPI or spin echo EPI? As we know, the balanced SSFP signal has some similarities to spin echo and therefore might be more sensitive to smaller vessels and less sensitive to larger vessels. That's why we did this research in this direction. But what you can see is that of course gradient echo EPI shows a larger signal change than SSFP, but the SSFP signal is somewhat, let's say, similar to the spin echo EPI, with the advantage that we don't have any distortions with this technique, and it's easily possible to acquire full brain coverage with balanced SSFP, which might be a problem for spin echo EPI at very high fields. And well, this is one example of whole brain imaging with balanced SSFP at 9.4 Tesla, you can see very nicely the activation. I think that's about a 2 or 1.5 millimeter resolution. And of course it's currently a little bit slower than gradient echo EPI because it's not such efficient as an EPI readout, but we are starting to test multi-echo SSFP, which then might come close to the imaging speed of gradient echo EPI. So what you can see is, of course, we are not completely banding free in a whole brain acquisition. You can see these typical banding artifacts in the frontal parts, for example. But if you compare this to a whole brain EPI acquisition at 9.4 Tesla, one could even say that the signal losses due to banding are probably even less than the signal losses due to signal dropout in EPI acquisitions. Yeah, that's all what I have to say at the moment. I think it's a very interesting technique, also about 15 years old, but it seems to be very stable. It gives a very nice functional contrast, and well, looking into the future, I think we have to explore well, what do we really see? What is the sensitivity of balanced SSFP to larger and smaller vessels and so on? And of course, how can we speed up imaging acquisition without loss of signal stability? Thanks a lot and goodbye.